Now there's another way of viewing these molecules that comes up, and we particularly see this quite often when we deal with carbohydrates and in biochemistry. But it's a topic that we should discuss, that we should be familiar with, and they're called Fischer projections. So Fischer projections have this defined kind of angle or view that we have to take when we look at the molecule. So what we typically do is we look at a molecule and we put the most oxidized form of carbon up at the very top. So for us, when we look at this structure, that means that this here, the COOH, that's going to be the top part of the molecule. Right? And then along the carbon, so this carbon's connected down here, and then back to this carbon, that is going to be your parent chain. So again, that chain's going to be from here and then back to this point right there. Right, so then that means that this atom and this atom are going to be coming kind of out of the plane when we look at this. And the way that we want to see this is we want to look at it really from down here. So like here's our eyeball. Now I've numbered these up above here. So the OH group here, right, that's number 1. Number 2 is the COOH group. Number 3 is the CH3 group, and number 4 is the H group. And what we're going to do, if you look at this top structure here, is we're going to rotate this thing around. And when we do that, we want 1, 2, and 3 to kind of be like the vertebra, right? They're like the backbone, essentially, of our structure, right? So there's vertebra number 1, number 2, and number 3. And along the central vertebra, we're going to have atoms that are going to be pointing out towards us. Okay, and that's going to be your atom number 1 and your atom number 4. Right, and then the convention is that we take these dashed lines and these wedges and we eliminate them and we draw them as just lines. That's different from a Lewis structure though, because a Fischer projection shows orientation or direction. Right, so it shows us the way atoms are pointing, essentially. So this is a drawing of that structure that we had on the previous page. So remember, we want to look down this bond right here. This top carbon is your COOH. This back carbon back here is your CH3. That's going to be your backbone. And what we want to do is we want to orient it just like this. Okay, so again, that's the angle that we're looking at it, right? So these bonds right here, if you look at it, those bonds along the horizon, right, do you see? They're pointing out at you. They're pointing out like a bow tie. So you can think of them as like a bow tie, or you can think of it as like a little person coming out trying to hug you. All right? Now this has important consequences for us as far as stereochemistry is concerned. Right? So when we go through and look at this, let's label this thing. Right? So 1 comes up to 2, and then around to 3. So it's moving around this direction right now. That is the R direction. However, look, number 4 here is pointing out at us, right? Remember a wedge? This is out. So then our R needs to be changed to S for that, right? So what you have here is S on the top, and then this is S down at the bottom. S, lactic acid. All right, so that's kind of the idea behind drawing these Fischer projections. Now, longer molecules are more complicated. Right, remember looking at this picture? This is our carbon backbone right now. Right, so if this was a CH2 connected to another CH2, it would actually bend down this way. So the molecule kind of bends around so that we're always positioning these atoms across this horizon in orientations that point out to us. So the general rule would be to rotate around this carbon-carbon bond here. That's going to put my chloro group back on a dash, and my H group will come out on a wedge. Now the top of the molecule we mentioned before, right, is the most oxidized form of carbon. So this is a pretty good general rule of thumb for determining who's on top. Now we want to look at the molecule from the top of this thing. And when we do that, we want to imagine that these are the carbons of our backbone. So here's vertebra number 1, number 2, number 3, and number 4. Okay? So as we draw that out, we're going to end up getting a structure that looks kind of like this. And let me pull this down a little bit. So looking at this molecule here, we have our chloro groups pointing out towards us. We've established that this is going to be the head, or the top. And what we have to do is we have to rotate this guy around. So we're going to take this, we're going to turn it around just like so, like that. Okay. So once we have that, we're going to have to swing this thing around and draw it like this. So that's what we're trying to draw here. That's our structure. So then what we're going to get in the end here is our CH2 up at the top. And then our OH there, where's the CH2OH, and then a carbon, and a CH3. And then remember, along here we have our bow tie, right, or the hugs coming out, getting us. And then we have off of here our chloro group. So we put a chloro group on the left-hand side and a chloro group on the right-hand side, and our two H's there. And then we don't leave it like that. We draw it with our just straight lines, right? Remember, so what we're going to do is we're going to write this out as a CH2OH, and then a straight line all the way down here to a CH3. And then a line and a line, and a chloro group here and a chloro group there with an H. And right, another H at that other position there. Now, we can check this. We should be able to check this. So sometimes students don't like this rotation thing. So what we can do is we can see what our stereochemical designation is at each one of these positions. So if we wanted to check that stereochemical designation, this would be 1, that would be 4, this side down here is number 2, up here is number 3. So that goes 1, 2, 3, this direction. That is the S direction, but we have to change this to R. And then down below, this would be number 1, and 4, and 3, and 2. So that's going 1 to 2 to 3. It's going also the S direction, but H is pointing at us, so we need to switch to R. So in our structure that we start off with, hopefully we have 2 R's. If we don't, then we just switch our Cl and our H if you wanted to kind of brute force this. So as we come up and look at our original structure, right, here's our carbon number 1 that we're looking at. So at this position, that's a number 1, that's a number 4, that's a 2, and this is a 3. So that's going around 1, 2, 3. This direction, that is the R direction. H is pointing away from us, so bam, nice. Coming over here, that's number 1, that's number 4, that's 2, and this guy's 3. So that's going around this direction. That also is the R direction, and H is pointing away, so nice. So we've confirmed that we've drawn the structure correctly. So sometimes students like to just determine this. So in other words, you figure out, is it R, is it S, right? You figure it out, in this case, both R, and then you come down here, and then you basically guess. So this would be the right guess, but let's just say that you put the chloro group at this position. So if your chloro group was there, then you'd have to, you'd end up getting the S confirmation. You have to switch to the other side to get the R confirmation. Now, a couple things to point out here too. When we compare Fischer projections with each other, there's all sorts of rules that are out there. So if you're starting off here in the middle with this S confirmation, if we do a 180-degree rotation, we get an S. Right? If you switch both horizontal and vertical, you get an S. If you rotate 90, though, you get an R. If you switch vertical, you get an R. You switch horizontal, you get an R. So those are some of the tricks of the trade as far as comparing Fischer projections. So one of the things classically that that comes up in these type of problems is you're given 2 or 3 or 4 different orientations or Fischer projections or just drawings, and you're asked to determine if they're the same or if they're enantiomers of each other. So just remember, when comparing Fischer, kind of the easiest thing to do is to do 180-degree rotations.